Welcome back to Math 104. In the last video, we computed each deviation from the mean for this sample of test scores from section 1, and then for each deviation from the mean, such as negative 10.2, we computed that number squared. So this is negative 10.2 squared equals 104.04. This right here is the squared deviation from the mean of this data point. For the data point 70, 70 minus the mean quantity squared is 27.04. Similarly, we get 7.84, 14.44, and 77.44. You should have obtained those values when you did this computation at the end of the last video. So what is the sum of the deviations from the mean? That is certainly 0. It is 0 for this data set, and it will be 0 for any other. But the sum of the squared deviations from the mean, that turns out to be 230.8. We can start to see why this number tells us something about how spread out the data points are from their mean. Because the points that were furthest away, the scores that were furthest from the mean, the 65 and the 84, are contributing a great deal to the overall sum in this column, whereas the scores that were closer to the mean are contributing relatively little. We've now computed that for this sample of 5 scores, drawn from a full collection of 100 scores in section 01, the sum of the square deviations equals 230.8. That's great. Now what? We've done the hard work. We still have 2 short steps before we're quite finished. If little k denotes the number of data points in the sample, which in this case is 5, then the sum of the square deviations from the mean, that's what we just computed, divided by 1 less than k, so in this case, that's going to be 5 minus 1 equals 4. Okay, so we take the 230.8 and we divide it by 4. That is called the sample variance. It is denoted little s squared. This thing in the numerator here, it may look complicated, but this is exactly the sum of the squared deviations from the mean. This is exactly what we tallied up in the right column of the table in the previous slide. That sum of squared deviations from the mean, which is 230.8, divided by k minus 1, which we noted is 4 here. There are 5 data points, but we only divide by 4 in this expression. That's how sample variance is defined. And this equals 57.7. This is the variance, the sample variance, for our set of 5 scores. This number is also some kind of measure of how spread out our 5 scores are from their mean. But we have 1 step to complete before we're really done. The square root of the sample variance is called the sample standard deviation, and it is denoted little s. This is why we used s squared for the sample variance, because what we're really after is the square root of that, which is just s. So the sample standard deviation here, this equals the square root of the variance, which is the square root of 57.7, and that is approximately 7.596. All right, now we've computed the thing that we need. It took a few steps to get there, but this quantity, the standard deviation, is going to be our main measurement of how spread out, how dispersed about its mean a set of data really is. The larger this number is, the more spread out the data. The smaller this number is, the less spread out. What if you had a data set that just consisted of 75, 75, 75, 75, 75? Well, then the mean would just be 75, and the deviation from the mean for each of these 75s would be 0. We'd be computing a lot of 75 minus 75 squared, which would also be 0. We'd be adding up a bunch of zeros, and we would end up with 0 for the variance and for the standard deviation as well. So if all the data points were equal to one another, there would be no deviation from the mean, and the standard deviation would be 0. If we played with these numbers and stretched them out even farther, the resulting standard deviation would become higher. We'll see this more clearly when we contrast what we just computed with the standard deviation for the sample drawn from the other section, where the numbers were more spread out. Let's do that now. Let's compute that standard deviation for the sample drawn from section 2. The sample mean is 48.8. just the average of these 5 numbers. Our goal is to find the sample standard deviation. We could set up the table as before, but let's see if we can go a little bit more directly, at least to the definition of the variance. So the variance, s squared, equals the sum of the squared deviations from the mean. So 31 minus 48.8, this 31 minus the mean squared, plus 41 minus 48.8 squared, plus, all right, etc. here. We'll do the same for 54 and 56, all the way up to 62 minus 48.8 squared. All that needs to be divided by k minus 1. 1 less than the number of data points in our sample. Whatever number this turns out to be, this is the variance. So the sample variance turns out to be 157.7. When we tally up the sum of squared deviations from the mean in the numerator, that turns out to be 630.8. After dividing by 4, that gives us our variance, 157.7. Before going on to the next video, answer the following questions. First, find the sample standard deviation for section 2. And then, how does the sample standard deviation for section 2 compare to what we found for section 1, where it was 7.5961?